Connecting to cloud server. All right, I guess that means it's recording. All right. So chapter 1, we're going to learn about matter, the very basics of chemistry. So atoms, molecules, and compounds. Now, a lot of you may think, oh, duh, that's really easy. But it's important to know the terminology before we start to learn chemistry. Terminology is very important, such as what's the difference between an atom and an element, stuff like that. So an atom is, when you're talking about atoms, it is the subatomic particles. It's the fundamental particles. Just an atom of oxygen, an atom of hydrogen, an atom of nitrogen. Molecules are when you take two or more of these atoms and chemically bind them together, chemically attach them, either by covalent, ionic, or some other means. And that's a molecule. So two or more of these atoms attached. Then a compound. A compound is a subset of molecule. So a molecule is any two atoms. It could be oxygen and oxygen, right? So this, we'll learn about Lewis structures later on in the class, but this is the Lewis structure for oxygen.
I'm still viewing the syllabus right now. I don't know if this is just a me problem or.
No, wait, what'd I do? Oh, Daniela also said the slides are not showing up on the screen. Oh no. Haha. How's that?
Yeah, that's better.
Good.
Okay. Definitely let me know beforehand. If you didn't say anything till like halfway through the lecture, that would have been fun.
Yeah, I thought you were just like talking.
Like
I didn't realize
you
you
were
already. Yeah.
So there it is. There it is. This is stuff. Okay. So atoms, you get it. Molecules, two or more. And this is the Lewis structure for oxygen gas. Is O and O next to each other, right? They're chemically bound covalently by double bond. This is a molecule. It is not a compound. A compound is when you have two or more different types of atoms or different elements. Oh, it says it right there. All right, of different elements chemically attached together. So, for example, NH3, CO2, things like that, they would be compounds and molecules. But an oxygen molecule, O2, the oxygen air that we breathe, will only be a molecule and not a compound. So does that make sense? Good. All right. All right. So chemistry, yeah, we're learning about how matter interacts. Yeah. Okay. We're gonna breeze through this stuff. So a hypothesis is you observe something in nature or in a lab, and it's your tentative explanation of how or why it happened. So if I see, oh, the apple, when I let go of the apple, it fell to the ground. A hypothesis could be there must be gravity. That's one. Another one that's equally valid until you prove gravity is that there is a magnetic force that's inside the apple that is pulling it towards the iron that's inside the Earth's crust. That's a perfectly viable hypothesis until it's proven wrong. So it's just basically an educated guess. Scientific law is when you have many scientists from around the world and they prove the same thing using different techniques, and you come to a consensus. But that consensus is for the time period, meaning laws can be broken when new information is found out. And this happens in physics all the time with gravitational waves, for example, that broke some laws. Not really sure exactly, but yeah. So a theory is basically if you have experimental proof in your own lab that leads to the suggestion that something is true, then it would be your theory. Oh, this is my theory because I did this, and this experiment. And you can propose an idea for it. But until that idea is tested by different experiments and other validation techniques, you can't say it's a law or it's a definitive fact. It's just a theory. All right, so let's do this. So my car has trouble starting on cold, wintry days. Is it a theory, hypothesis, or observation? Somebody could answer. Actually, you can write it in the box if you want. I don't know how this is going to work. I guess write it in the box. Okay, good. Observation. Not everybody should write it in the box, but I guess a couple of you. but I guess you won't know which one of you is the couple of you. But anyway, just, I don't care. Observation, good. My car has problems starting because of a faulty spark plug. Is that a theory, a hypothesis, or an observation? Oh wait, what did I do? No. So did you test that? So people say theory and some say hypothesis. Now, a theory, what do we know? Theory is a general explanation of why something occurs, of why the behavior is, and it can be validated. So I guess that's why your car has trouble starting, but you didn't do any experiments to see it has a faulty spark plug. That's your hypothesis is, oh, the reason why it's happening, it could be a faulty spark plug. So then it appears that that model, I keep going to the next slide. You can see the answers. So it appears that all the models of those Juno cars from the year 2010 have the same problem. There was a faulty spark plug installed in that year. So that would be a theory by process of elimination, because that theory was tested or some searching was done on it to see, I found the clue, which is from that year, they all had faulty spark plugs. Therefore, that is the truth, and that is your theory, because you have some evidence to to suggest that theory, which is you Google searched it and you saw that that problem exists. So there we go. Okay, so that stuff, I don't even think there's a question on it, whatever. But here's where we get into real chemistry. So matter. So matter is composed of anything that occupies space. I matter, you matter, we all matter. Haha. Right. Also, I'm going to make jokes and they're terrible sometimes, and just bear with me. I hope I don't offend anybody, but I probably won't. But I don't know. I hope not. It's like that nerd joke I said before. I didn't mean to offend you if you got called a nerd all through school. I did. So, but now I'm proud of it. So you should be too. Okay. So we can classify matter according to its state and composition. So a state meaning solid, liquid, or gas. Composition meaning what is it made of, meaning chemically, elementally, what is it made of? So before we get into that part, we're going to talk about the different states of matter, their physical states. Now, this graph is important to understand the different states. And I want you, I could sit here and rattle off solid, liquid, gas. Solid is solid, the liquid is liquid, and the gas is gas, duh, right? But I want you to have an understanding of it in an energetic point of view. And what I mean by that is this graph is a heat diagram, a heat phase diagram that shows you the transition with temperature and energy. Someone just showed up late. Okay, whatever. So this graph shows the composition or the transition in physical state from solid to liquid to gas. So if you start out with a solid in ice, the point is here that an ice or anything with a lower temperature is at a lower energetic state, meaning the atoms and the molecules that are in that substance have less speed, they have less energy, and they don't move as much. So they're rigid. That's what makes the rigid solid formation of any solid. It's the low energy particles. There's not much velocity. They're not really being energized by thermal energy or any other kind of energy. So low energy. Then once you increase the temperature or increasing the thermal energy, you get to a point known as the melting point, where that ice begins to melt. And you get at 0 degrees Celsius for water, you have water and ice mixture until all of the ice is turned into water. Once it is, it can raise temperature again. So what you're doing is you're increasing the energy, and that speeds up the molecules. In other words, it gives them more degrees of freedom. So if you increase energy, it makes the molecules faster. It gives them more degrees of freedom, which then makes them transition state at their specific points, their boiling and melting point. So, and that's characteristic of each substance. Water, we know, is 0 and 100 Celsius. Other things might be different. Methanol is at 67 Celsius for boiling. But every substance has its own characteristic melting and boiling point. And then as you increase the temperature of water, increase the thermal energy of water, you get to another point, the boiling point, which you have a combination of water and steam. And those particles of the liquid are gaining so much energy that they're excited to the point where they actually are emitted from the liquid and as a gas. So they have a three-dimensional degree of freedom. They can go up, down, left, right, back and forth, and they take up the space of their container. And then you can heat up a gas really indefinitely, and those molecules will just keep going faster. Okay, cool. So it's just equating energy to phase transitions. All right, so this is basically what I said. Increasing energy increases your freedom of the molecule, and temperature is directly proportional to kinetic energy, so the speed of the molecules. All right, so solids, there's another chapter to go over this, but basically there's two types of solids. There are crystalline solids where there is a pattern, there's a distinct pattern, and we're gonna learn about lattice structures. Now a lattice structure, let's say of NaCl salt, table salt. The NAs and the CLs are arranged in such a way that gives it a specific rigidity. And they're arranged with pluses and minuses kind of orienting in such a way, and it gives them a matrix, a lattice matrix. And that's what you see on the right over here is an example. I should know that you don't see that. Oh yeah, you do see that. That's a diamond. Okay, yeah, that's exactly what it is, that matrix. Then you have amorphous solids. So amorphous solids are just a blob, basically a blob of stuff that does not have any specific arrangement, like plastics, different polymers. Sometimes there's no arrangement. They just kind of stacked on top of each other in different arrangements and different configurations, and there's no real flow to it. There's no real pattern to it. So those are just two types of solids. Liquids, we know how liquids behave. They have a fixed volume, but not a fixed shape. That's it. Gas. So the thing that's different about gases is we know that as you increase the heat of a liquid, get above the boiling point, you have now increased the speed of the molecules to the point where they can be released from the solution as a gas and have more degrees of freedom. We're going to have a whole chapter on gases, but the most important thing is that they are compressible. Making them compressible, that means they have another variable to worry about when you're talking about a gas mixture, and that variable is pressure. You could also have pressure of a liquid and pressure of a solid, but in calculations they don't really come into effect, at least with this class. So, but gases, the pressure of the gases directly affects how they interact with each other and their forces and their volume, their temperature, all of those things. So, and we'll get to that in chapter, I don't even know what chapter, but they're compressible and they can take up the space of whatever container you put in them. So if you breathe, well, let's use a funnier example. If you fart, right? Why doesn't it smell after 10 minutes? Hopefully it doesn't, right? The reason why is because that gas disperses through the air equally. Let's say it's the room, it equally. So you don't really have it concentrated and it disperses. It's still there, but it disperses. So I hope you got a laugh out of that one. There's a little, here's everything, different states of matter. All right, so now let's categorize this matter. Now, this is a really good, this breaks it down. I'm gonna explain this right here, and then you can look at every all the other notes later, so, on the next part. So basically you have all matter, right? Out of all matter, you have substances. Substances are considered a pure type of composition, pure composition. Those types of things with a pure composition are either elements or compounds. So an element, such as gold, if you have a bar of gold that's 99.9%, let's just say 100% pure gold, every single one of those atoms, no matter which sample you take, is going to be gold. It's going to be a gold atom stacked to a gold atom, gold atom, gold atom. That is an elemental form of an element. Yes, an elemental form of a substance. Another example that you see around the house is aluminum foil. So aluminum foil, or even if it was actually tin, it's aluminum, but if it was actually tin foil, tin, that would be an elemental form, because it's 100% tin, you like to think. Then you have a compound, which is also a type of a pure substance, because the composition of it is equal all the way through. And it consists of the molecules that are in those, or the molecules that are in it, right? So for, in this case, like the compounds, let's say water. If you have distilled deionized water, the purest water, you have H2O here, H2O here. They're just all clumped together. They're all H2O, and it's compounds. It's not an element because compounds have multiple elements in them, like we talked about before. So so if you're wondering, let's say you had O2, right? So oxygen gas would be an element, right? Because it's not a compound. So O2 also falls into this category. Even though there's two elements chemically bound together, where there aren't here, they just kind of, they're not chemically bound together, they're just energetically bound together based on their distance from each other. The O2 would still be considered an elemental form of oxygen because it's a molecule that just consists of oxygen in this case. Okay, then you have mixtures. So mixtures are not pure substances, obviously, and they have a combination of things. So homogeneous mixtures are a mixture that is equal throughout the entire mixture. For example, if I take this section and this section, they're going to have the same amount of stuff in them. And that's a random circle, but I think it works. Let's say you have 1, 2, 3, 4 of those blue ones, and here you have 1, 2, 3, 4, and let's just look on one surface, and you have 1, and you have about 1, so it's about the same. The idea is there's billions of atoms here, not just a couple hundred. So over a normal sample size of grams, even milligrams, picograms, it would still be equal composition throughout. So that's a homogeneous mixture. So things with equal composition throughout. For example, salt water, sugar water that the sugar or salt is dissolved in. Then you have a heterogeneous mixture, which is the craziest, most realistic type of thing, right? Because that's what we deal with every day. By realistic, I mean the most readily encountered in our lives, right? Any food you eat is a heterogeneous mixture, unless you get a blender and blend it really, really well. But yeah, so most of them are heterogeneous mixture. A salad, great example. Or Zoom chat's in the way, I can't see this. What is it? He's sifting through, he gets gold and water put together. Oh, so that's kind of comprehensive. So his gold and water mixed together, but the gold is not interacting with the water. So once you sift through them and separate them, you can separate that heterogeneous mixture and get the gold out. So that's the idea there. Okay, any questions on that? No? Okay, cool. All right, moving on. Classification, we went through this already. Transforming matter. So we can change the state of matter, the physical state. And we can change the chemical state. So there are two types of... Oh, yeah, what's up?
Should you always be able to separate a heterogeneous mixture?
Should you always be able to? For our intensive purposes, yes. There's a lot of different separation techniques where you can do that. And you can even separate homogeneous mixtures. So yeah, everything, yeah, I'm gonna say 99% sure. Everything you can separate, heterogeneous or homogeneous, by some chemical technique.
Okay, thanks.
Okay. I'm thinking really complicated, like isotopes you can separate doing mass spectroscopy. That's the most difficult. And obviously a salad, you can go through and get every little crouton and stuff like that. But yeah, you can do that. Okay, good question. All right, so matter. So what we're gonna learn now is to identify different changes in matter. And there are two types of changes in matter. There's physical changes and chemical changes. So a physical change, we already learned about physical states, meaning solid, liquid, and gas. So a physical change has to do with those, in which the composition of the compound or substance is not changed chemically, but the physical state of it is changed, for example, from solid to liquid, from gas to liquid, etc. It can be reversed because you can boil water and then it recondenses when it loses its heat, for example. That's how you get dew and stuff. And if you cook the pot of rice or anything with boiling water, you see that the gas leaves the water and then recondenses on the inside of the lid and then goes back down into the liquid. That is a great example of how a physical change occurs. Also, physical changes occur by changing the shape of something. So if you cut a piece of paper in half, each piece of paper half is still paper. Chemically, it's still carbon and whatever else they add to paper. So yeah, that's physical change. Then chemical change. So a chemical change is where the atoms or molecules are rearranged into new atoms and molecules. So an example that they have here is really this encompasses every chemical reaction. Chemical reaction is the definition of a chemical change. For example, you have sodium metal and chlorine gas. They react together to make sodium chloride. So that's a reaction you can do in a laboratory. So they can only be reversed by other chemical reactions. So you change from one thing to another chemically, you have to change, you have the ability to change the other way chemically. So that's that. Okay, the physical change, we saw that already, chemical change. Common examples of chemical changing is rust. So you'll see that in the homework, you'll see that in tests maybe. So rust is a form of oxidation. So what happens with rust is, I'll explain that real quick. You have metal, so Fe. Now, oxidation is a process that occurs that degrades really anything. It degrades a lot of things, even degrades your body. Oxidation for your body is not very good. But for iron, and it's usually oxidation, the word has oxygen in it. So it means it has something to do with oxygen. So what happens is oxygen from two sources, the air and water, are going to come into contact over time with iron if you leave it outside in the elements, mostly water. The oxygen gas, it does affect it, but not much. So you have your iron molecule, iron atoms on the surface of, let's say you have a bike and you left it out in your backyard for a year. You're going to come back and it's all rusted. This is why. So the oxygen will interact with the iron because every oxygen, well, not this one, not really, but this oxygen is partially charged, and we'll learn about that. It's partially negative charge. And oxygen is a pretty strong negative charge. It likes to attract positive charge things or to attract other metals, which are mostly positive charge. And iron happens to be one of those positively charged metals. So over time, as water gets a chance to sit on this iron and just chill there like that, the oxygen will start to bind chemically to the iron, and it'll create a bond. That bond is a new chemical substance. It goes from iron and water to iron oxide, which is right here. That's Fe2O3, like that. So this is iron oxide, iron 2 oxide, iron 3 oxide. And this is what forms from oxidation. And this is what causes that rust color. So, and then hydrogen gas is released. So yeah, that's how it works. Cool. And there's other things, baking. So for those of you who said I think one or two of you said you like baking, or one of you, maybe it was Olivia, I don't know, one of you guys. But whoever likes baking, you are doing chemical changes because you are breaking apart bonds with heat, and you are creating new bonds and expanding the chemical structure, and you're actually making new bonds. So another example I give for chemical change is ask yourself, can you unbake a cake? You can't unbake it, right? Because you already chemically changed the bonds that's in the batter by breaking them and then reforming them differently. So yeah, cool. Okay, so there's examples of physical and chemical changes. You have dry ice sublimating. So sublimating is a rare physical change that you go directly from solid to gas, and that's one that happens. And dry ice is a good example. So it's solid carbon dioxide. When you expose it to air, it looks like there's gas coming off of it, and that's because there is gas coming off of it, and it's sublimating, going directly from solid to gas. And it's fun to play with too, dry ice. You could, it's so cold that me in my lab, what I do is, and my colleague, we rub it against the table so it's really smooth on the bottom, and it's so cold that it kind of hovers over the table, and you can play kind of like air hockey with it, and it glides across the floor. So it's pretty cool. So sugar dissolving is a good example of a physical change because you're not changing sugar. Another person is added. All right. So you're not changing the sugar at all. You're just changing the state of it. It's in a solid before, and you are making it into a solution, into a liquid solution after. And then propane burning, anytime we see burning. So the key words here, I'll write them down. For chemical change, my pen. Keyword for chemical change, you have rusting, burning, I guess I'll put baking. And yeah, those are the big ones. Are oxidizing, tarnishing. So tarnishing is very similar to rusting, but it has to do with silver. Okay, moving on. So we have energy. So energy. We're gonna go into a whole chapter with energy, but basically, energy is, there's different types of energy. There's energy where, well, basically the definition is the capacity to do work, right? And what work is, like working out, but it's basically when you move things over a distance against a force. So, or using a force, meaning it has to be against a force in the first place. So the formula for work, which we'll have a chapter on, is work equals the force times the distance. So there's got to be some force involved that you're applying to something, like this guy here. That's going to be me when I move to my apartment, my new place. But the box isn't going to be that big. That box is the size of him. That's crazy. Okay. And then over a certain distance. So we're not going to really cover that too much now. It's just intro stuff. Then kinetic, there's two types of energy, kinetic energy and potential energy. Now, kinetic energy, I mentioned it before when I talked about the different states. When you go from solid to liquid to gas, they increase in kinetic energy. In other words, they increase in motion. So the more kinetic energy something has, the faster it moves, and the more likely it is in a higher energetic state, probably a liquid or a gas if it has a lot of kinetic energy. Potential energy. So is the energy associated with the position of an object, or position or composition. So for example, the best types are, or if you hold a book, hold anything in the air, and then you remove your hand. That is a prime example of the conversion of potential energy to kinetic energy. What you're doing is at first, because whatever you're holding has a certain height in the air, it has a certain potential energy. It didn't have the energy yet. It's just a potential energy. Then all of that energy will be released into kinetic energy once that object is dropped. And you can see that happen. And chemical bond energy is another type of potential energy. So a great example of chemical bond energy, nuclear we'll talk about in another chapter, but chemical bond energy is food. So where do you get energy to do anything? It's from your food. And the bonds that are in food are broken down into useful amino acids and other chemicals that help us move and help us do everything. Every metabolic process is dictated by your food. So this energy that helps you do what you do, or helps your body run, is stored in the chemical bonds. And when those bonds are broken, your energy can be used, and those molecules can be utilized as energy. So, okay, cool. And that's potential energy because it's not dealing with moving particles. All right, so you have two types of properties. I'm not going to test you on this. I'll just go over them. So, because I know this chapter is all over the place. I don't like chapter 1. It's like all over the place. And I feel like I do it worse every year because I assume you know more than you do. But if I'm going too fast, let me know. So an extensive property depends on the amount of matter. So meaning if you have energy, right, that depends on what you're dealing with. It depends on what's the energy of, like E equals MC squared. What's the energy, or what's the mass, or what are you dealing with? Are you dealing with a pencil or a truck, right? So it matters the energy, because basically if the amount of matter, right? Amount of matter, that's called mass. If mass is in the formula and it's not being divided by anything, it is definitely an extensive property. Force, F equals ma, if you know physics, right? So F equals ma, the force depends directly on the mass. So that means it's an extensive property. Intensive properties, on the other hand, they don't matter, or they do matter. They don't depend on the amount of matter present. So density, the formula for density is m over v, mass over volume. But even though this has mass in the numerator, it's the mass per unit of volume. So it doesn't matter how much mass you have, the density will be the same, because of that substance, the volume will move accordingly. So if you have a 1 gram substance that has a 1 gram per 1 milliliter density, if you have 100 grams of it, the density will still be 1 gram per 1 milliliter. And your milliliters would then be 100. So it'd be 100 grams per 100 milliliters. So that property is the same. And the matter, and it doesn't really depend, the property of density does not depend on the mass of the substance present. I hope that makes sense. All right. So intensive or extensive. All right. So work done on the object. Intensive. I guess I'll just go through this. You don't have to answer these. So work done on the object. So it is going to be extensive because it matters. The object matters, right? So it could be a heavy object. In that case, a different amount of work needs to be done. Density, we just talked about as being intensive. Water freezes at 0 degrees Celsius. That would be intensive. It doesn't matter how much water you have. It will always freeze at 0 degrees Celsius. So just, yeah. Well, look at that. I'm so smart. Okay. So we did that. We talked about those. Density, we talked about. So density has different units. And it's important to know density. So it's mass per unit volume. That's the general formula of it. But there could be several different units specifically for it. For solids, we like to use grams per centimeter cubed because you can measure a centimeter cubed on a solid better than you can a liquid. But a centimeter cubed is the same thing as a milliliter. So grams per milliliter. What I usually use is grams per milliliter, or really milligrams per milliliter, but that's for small volumes and small, very low concentrated things. Now, a centimeter cubed is equal to a milliliter, which is equal to a cc. That's the same thing. These are all the same unit. So I teach nursing students in the city, and this is one of the first things I teach them is when they say, oh, nurse, give me whatever 5 cc's of that, they mean milliliters. They're just trying to sound cool. So it's centimeter cubed, milliliter, same thing. And for liquids, we use gram per milliliter usually. For gases, we use grams per liter, because usually you deal with liters of gases, not milliliters, because it is dispersed over a larger volume. Density, we should understand that as you increase the energetic favorability, as you increase the energy of different states of matter going from solid to liquid to gas, the density decreases. So that's mostly true, except for water, which I'll explain in a second. I don't know why I crossed that out. Control Z. So that makes sense, right? There's more movement, there's more expansion as you go from solid to liquid to gas. And that's why there is lower density with gases, which is why you need a bigger unit. You need per liter, not per milliliter, to get a tangible number for this value. That's because gases are so undense, not dense. But except for water. So except ice is less dense than water. All right, and then you can test this at home is, well, let's go over the reason why. Well, there's different ways to test it at home. But basically, liquid water, you have a water in in a bottle, right? You put it in the freezer, you freeze the bottle. Sometimes the plastic breaks, and that's because ice expands its structure when it's frozen. So it goes against the rule that most substances follow, where as you increase the energy of the solid, it goes to a liquid and the molecules or atoms expand. Water does not do that. When you go from solid ice to liquid water, the molecules actually compress. And the reason why is because of the hydrogen bond. So the hydrogen bond, so here's water and here's another water. Do that. And the hydrogen bond is not a intramolecular bond, it's an intermolecular bond. And we'll learn about what that means in later chapters. But basically, it is a bond that occurs between two water molecules or more. It could be more water molecules. There's hundreds around here. That creates them, that makes them, makes the structure pretty rigid, right? And they bond to each other. This also occurs in liquid water, but liquid water is at a higher energy state. That energy state can readily break these hydrogen bonds and reform them quickly, because the liquid water has more energy than the ice. If the liquid water can therefore break these bonds more easily, you can imagine if this bond wasn't here, the molecules would be bumping into each other. They'd be smushing against, bumping into each other, bouncing off of each other, and moving around like a gelatinous substance. That's exactly what water is. It's a liquid, but if you look at it molecularly, all you have is molecules hitting into each other. So that actually compresses the structure of liquid water in comparison to ice. Because in ice, these bonds, these chemical bonds, these hydrogen bonds, are going to be conserved, and they're going to stay like this and be rigid. It'll make the entire structure, molecule 1, molecule 2, molecule 3, they'll be rigid in a type of lattice like we talked about before. It doesn't look like this at all, but like some kind of pattern where you have molecule, molecule, molecule. If you increase to a liquid, what I'm saying is this will break, 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 break. All these bonds will break, and then that allows the molecules to come in close contact with each other and actually be compressed in comparison to the ice. That's why water is very unique, and it doesn't work out like normal substances do. Okay, any question on that rant about density and water? No? Okay, continuing. Density, we get it. All right, let's calculate some density. So let's do this. So calculate the density of a ring with a mass of 3.15 grams that displaces 0.233 centimeters cubed or milliliters or cc of water. So I guess I'll give you a minute or so or less, and you can write it in the chat box, the answer. B. Yeah, makes sense. Probably B. All right, cool. Probably B. And it's B. Wow, so smart. Everybody's really smart. Good. Okay. Now for temp, we didn't even talk about temperature yet. I don't know why this is on here, but it's important. So temperature. Are we gonna get the temperature? I guess not. That's in the next chapter. Wow, I don't like the way these chapters are written. Anyway, so temperature. There are 3 units for temperature. There are Celsius, Fahrenheit, and Kelvin. So Celsius is what we use in chemistry sometimes. Kelvin is what we use, is our SI unit, is our very specific unit of standard unit of temperature. It's called Kelvin. And Celsius is here, and Fahrenheit, I can't even spell Fahrenheit. That's probably it, something like that. So, oh, I suck at spelling, by the way. I'm atrocious. I should just stick to science. So basically, what my point is here is that we're not going to ever use Fahrenheit in chemistry, ever. And the reason why is because the scale is actually different. Like, oh, no shit, of course they're different. No, but I mean, the units are different. So what I mean by that is 1 Celsius unit is equivalent to 1.8 Fahrenheit units. So you can't easily convert from one to the other and use that in an equation. Celsius to Kelvin, you can do that because the Kelvin scale is basically just a Celsius scale moved over. So each unit of Celsius is 1 unit of Kelvin. And here's the formula for that equation, for that conversion. Celsius plus 273.15 equals Kelvin. This will be given on the exam, and anywhere, any chemistry class you take, this will be given on the tests. And it's a very easy one to know. You take Celsius, add 273.15, and you get Kelvin. So what's the answer to this one? Oh, it's there. It's C. Yay. All right, cool. So 40 plus 273 is 313.2. All right. So the reason why they made Kelvin, or how Dr. Kelvin made it. So what he or she, I think it was a he, did was he did some calculations, and he was like, all right, let's see energetically how slow can a molecule go? Meaning, how much energy can you take out of the atoms until they stop moving completely? Since temperature is proportional to energy, this is a good question to ask, and this is where temperature comes in. So they did some tests and were like, all right, how? So they're like, okay, I did calculations. Turns out that negative 273.15 Celsius, negative 273.15 Celsius, is the coldest that anything can get in the universe. This is called the absolute 0 point, meaning everything has energy. If you take out every piece of energy, everything, the temperature of it will be negative 273.15. Realistically, that is not possible to take out all of the energy. That does defy some laws of physics. I don't really know exactly what, but that definitely affects. That would, maybe a black hole would form and we'd all fall in. I don't know, but that is called the absolute 0 point that can really never, in my opinion, can never really be reached. So what Kelvin did was like, oh, I found out this negative 273.15 is the limit. I'm going to make my own scale based on that, just so my scale has no negative numbers, because some people aren't good at math in 1750 or whatever he made this. So I'm not going to confuse them, and I want all my numbers to be positive. So he's like, all right, I'm going to start at 0, and I'm going to go to infinity. Celsius goes in, the Celsius scale is from negative 273 to infinity. So Kelvin's like, I'm going to change this just by shifting over the Celsius scale by 273 units. And that's exactly what he did. Now, a good question would be, Professor, what is the coldest anything's ever gotten? Well, I'll give you a example. I'll give you a comparison. Okay, so 0 Celsius is freezing. It's water, freezing water, and it's pretty cold for us, right? So 0 Celsius is going to be 273 Kelvin. So 273 Kelvin is pretty cold. Subtract a little bit from that, you get to like, subtract 70 degrees, you get to 200. That is probably the coldest temperature ever, is 200 Kelvin on Earth. On Earth, sorry, on Earth. And maybe Siberian tundra or something, like in Russia, where it got to a crazy cold temperature, 200 Kelvin. If you go to space, like even around Earth, 3 to 4 Kelvin. Extremely cold, so cold that even with the sun there, it's that cold. Or maybe 5, maybe 10, 3 to 10. Still, the idea is that it's way cold, super cold.
They get
like
lots of computer chips really cold.
Yes. Well, you need to keep your computer chips really cold.
No, I was like watching a video yesterday, and they get quantum computer chips down.
Oh, quantum. Yes, quantum.
Yeah, fractional Kelvin.
Right. Yeah, so they use liquid helium cooling for that. So liquid helium actually operates at, I think, 1 to 3 Kelvin. Maybe they use other techniques as well, but I know it's 1 to 3 Kelvin is liquid helium. And they use that to cool quantum computers, like you said. I don't really know too much about that, but I know it's that temperature. So cool. So this is a space. Deep space, like in Pluto, whether you believe it's a planet or not, it's like 2 Kelvin. The coldest something's ever gotten, ever, is actually on Earth in a laboratory in MIT. And they did an experiment to, I don't exactly know what it was, but they drew out all the energy of only a few particles, only a few atoms. And they got it down to 0.1, 2, 3, 4, 5, 6, 7, 4. They got it down to this. Basically 0 Kelvin, and it's not 0 Kelvin, but they got it down to almost a billionth of liquid helium in this experiment. That's crazy. That's insane. And actually, we can say that out of everything in the known universe that we know, human beings created the coldest thing ever. We can say that. Until the aliens come, then they're going to say, no. We reached 0 Kelvin 2,000 years ago. You guys are just catching up. So, if you
as of right now, we're the chillest, right?
What's up?
As of right now, we're the chillest.
We are the chillest in the world. Yeah. So we're so chill right now. All right, good. So I hope that makes sense, and we're gonna move on. All right, precision and accuracy. So we'll go through this kind of quickly. So precision, how repeatable a measurement is. So darts is a great example, which is in the next slide. And accuracy is how close your measurement is to its real or expected value. So let's look at these dart. Before we look at random and systematic error, I'm not going to really test you on this. It's just different types of error. But let's look at the dartboards. So the dartboard A, it's really terrible. Whoever shot this must have been drunk, or they just were not very good at darts. And basically, this is, if you're aiming for the bull, let's say the bullseye is the true mark that you're trying to get. This is not accurate or not, and not precise. They're far away from each other, and all of them are far away from the goal. So that's neither. Let's say you have B. B, let's say this just means you're off. You're pretty good at darts, but you're making the same mistake over and over again. Maybe you're pulling your arm more to the right, or whatever. There's a little bit of angle off there. This measurement, if you're aiming for the bullseye, is precise because they're all near each other, but it's not accurate near your goal. This is what we call a systematic error. So a systematic error, I get that all the time in my experiments, where I'm expecting a certain value, but based on our instrument, it just happens to be a little bit off. But it's consistently off at the same value, meaning we can trust it. Random error, we can't really trust this kind of error because it creates a large standard deviation and our data is not very reliable with it. That's why we do always duplicates of experiments. But if we get a systematic error that keeps occurring and we can just adjust all the error at one time, we can use those calculations in real science. Then you have the best case scenario is where you're accurate and precise. So which means you're all in the bullseye and you're very good at darts. Okay, so this is just more examples of it. You can pause this later in the video, when you get it on YouTube, and you can take a look at when you're studying, but just different things I just mentioned. Okay, so separating, not really too, well, we'll go through it. So this gets to your question before, I forgot who asked it, but can heterogeneous mixtures be separated? And the answer is yes. I think mostly everything can be separated. And there are different physical and chemical techniques to separate. A physical technique would be distillation. So distillation occurs, let's say you have water with salt in it and you want to distill the water. What happens is you put the water in a flask, you heat it up, the water vapor travels through the distillation tube, goes through the condenser, and this condenser has cold water, it's liquid cooled. So it has water going around the tube to actually cool down this gas that comes in, the water vapor, cools down the vapor, makes it recondense into water. That water drips down into the receiving flask. So it's a very common organic chemistry experiment. You're going to be doing this a lot if you do organic chemistry. So Carlos, you said what would happen if you touched it? You touched what? The flame? You would be violating the lab safety video, and you would have to watch it again probably. That lab safety video sucks. So if you ever took chem lab, yeah. Oh, the coldest object. Oh, sorry, that was at 10:30. Oh, you said it now. Okay, so good question, Carlos. What would happen if you touched the coldest object that, let's say, it was bigger? It was only a couple atoms, but let's say if it was like something tangible. If you've ever seen the movie Snowpiercer, that's what would happen. If you haven't seen it, that doesn't make any sense to you. Basically, there's a scene where there's an apocalypse, there's an ice age, the earth is like super cold, you can't go outside, and there's this one train that has all the people that are alive in it, and they have their own society, and it's kind of like a rebelling against society movie. But in the beginning, they torture a guy for driving. He did something stupid, whatever. They put his arm outside the train. They made a hole. There's a hole in the train window. They put his naked arm out there, and it froze off. But it wasn't 0 Kelvin. It was pretty damn cold. But it became literally just ice. All of the atoms and molecules and blood in that arm that was exposed to the elements, to the really, really cold environment, froze in place, and his arm broke off like an icicle would of a house. So that's what would happen. And the amount of pain, you wouldn't even feel it. At first, you might. If it's in the movie, they felt it. It was like excruciating pain. But if it was the thing at MIT, the 0.0000 whatever Kelvin, you wouldn't even feel that. It would happen so quickly that you wouldn't even see it happen. It would just be instant of your arm just turning to ice. But if you touched it, it would probably happen to your whole body. You wouldn't even be able to get close enough to touch it before your body would start to freeze. So I hope that blows your mind. That's crazy. Snowpiercer, good movie. Kind of violent, but if you're into that, whatever. Good.
Do you watch Rick and Morty?
Yeah.
I like the little Snowpiercer spinoff.
I didn't see that episode. I've seen I haven't watched everything all the way through. I've seen most episodes, but I don't remember that one.
It's like one of the really new ones.
Oh, okay, maybe that's why. All right, I'll take a look at that. Cool, extra credit for you. All right, moving on. So filtration is another type, very simple type of separating mixtures. You have a filter, you have solid particulates in a liquid. The solid particulates are stuck to the filter paper, and the liquid passes through. All right, so now the SI units. Now, these units are standard international units for science, and there are several of them, 4 of them which we need to know right now, the basics. Length is in meter, mass is in kilogram, not gram, very common misconception. Time is in seconds, and temperature is in Kelvin, not Celsius. Now, these units are very similar to the metric system. Metric uses meters, kilograms, seconds, but it does not use Kelvin. It uses Celsius. So can anybody tell me which unit? So between the 3 scales, you have the US weird units, right? Inches, feet, whatever. Then you have the metric system, which is the UK and everywhere else except for here. And the SI units, which are everywhere. What is the one unit that has the same, well, what is the one quantity that has the same unit for every one, for all 3 scales? Yes, time, good. So seconds. I kind of just gave that away almost. So seconds, nobody, there's no unit of measuring that measures seconds in seconds or something. There's no like weird like offset unit like that.
Globally, we just decided it wasn't worth the headache.
Exactly, and especially for time differences, for flights, for like international, any business internationally would be destroyed from having a different, or be made really, really complicated. If they had a different, what was that?
Imagine it wasn't like a 1-to-1 conversion the same way Fahrenheit doesn't convert to Kelvin.
Yeah, it's like you're like, oh, and like the hours were different. It was like oh, your hours to lowers. You have to like multiply by 15 and then subtract some constant or something. Like that'd be nuts. But yeah, so it's good that we all use the same measurement for a second for time. Time, cool. Temperature, we talked about temperature a little bit. So the higher temperature, the larger average kinetic energy. In other words, temperature is the average amount of kinetic energy. It's a measure of it. So the more speed of your molecules, the hotter they are, the more thermal energy they have. Celsius to Fahrenheit. So here's what you're talking about with this crazy formula. It's not too bad, but I don't expect you to memorize it. It will be given on the exam. And well, on the exam, you also have resources. You can, yeah, but whatever. So the Celsius degree, like I mentioned before, is 1.8 times larger than the Fahrenheit degree. In other words, 1 degree Celsius is equal to 1.8 degrees Fahrenheit. So wait, no, I said it the opposite. 1.8 degrees Fahrenheit equals 1 degree Celsius. Yes, that's correct. Okay, wait, did I say?
Yeah, you were right the second time.
I think it was the
Okay,
second
okay.
time
Oh,
because
the second time. Yeah. Okay.
yeah, Celsius
Yeah.
is always lower than Fahrenheit.
Right. And the Fahrenheit, the units are, the numbers are larger, I guess. Whatever. If you understood, yeah, exactly. 100 Celsius is 180 Fahrenheit. Okay, take that as you will. I know what I'm talking about, but sometimes I just can't say it. Okay, so good on temperature. Now Kelvin versus Celsius, we talked about that. There's the formula. Prefixes. Now, I expect you to know some of the prefixes, not all of them. I would say from, in today's world, since we're dealing with terabytes now, more common, tera all the way down to pico. You should be familiar with. But I don't really, yeah, actually that's good, yeah. We don't use hecto or deca. They're not in here anyway, so good. We use them, but we don't have to use them in this class. So anyway, be familiar with these prefixes. So pico, like picograms, right, is 1 trillionth or 10 to the negative 12th of a gram. So picograms are extremely small. Nanograms is 1 billionth. Micrograms is 1 millionth. Milligrams is 1,000th. Centigrams is 100th. Decigrams or deci is 1/10 of a gram. Kilograms are 1,000, right? Like if you watch like the Drugs Inc. or anything, like, oh, a kilo of Coke or whatever, Breaking Bad, whatever. They talk about drugs or anything could be in kilos. That's kilograms. So 1,000 grams. Mega and giga and tera, we really don't use in chemistry. No one says megaliters or like gigakelvin. Well, they do use gigakelvin in like physics, but
I have a question.
Yes.
How come micrograms and altigrams are used interchangeably?
Micrograms and what was that?
Like UG.
Oh, and U. So UG is micrograms. This is the Greek letter mu, which also means micro, but people just write UG.
Okay.
Yeah, good question. So a lot of most of these are just letters, except for micro, since M is already taken by milli, and big M is taken by mega. It's the Greek letter mu, and they just put that in front. Sometimes in my presentations and in a lot of scientific literature, they actually just put U instead of mu because they're actually too lazy, and I do this too, of going to insert symbol on word and getting the mu. So they just write UM, micromolar, or UG for microgram, stuff like that. So yeah, that's one of the units. And then usually for computer space, we talk about giga, tera, mega, giga, and tera. So that's good. Oh, also I forgot to tell you about one of my hobbies. So I build computers. I build gaming computers, and I have my own little company. So I'm not trying to sell to you right now, but if you need anything, I'll hook you up. So anyway, let's move on. So density and volume, we talked about that already. All right, the last thing I think. Okay, two last. Now it gets into sig figs and then unit conversions, and then that's it. So it'll probably take another 45 minutes. Oh, Chuck, what is it? My company? I'll give you the link. All right, don't get derailed from chemistry though, because we're still in class, even though it's remote. All right, so sig figs. Now, I'm just gonna cut to the chase here. Sig figs are a pain in the ass, but they're important because we need to know how to make measurements. Let's say you have a ruler, or let's say you have a burette, right? And we need a correct way to measure it. So let's say the liquid level of this burette is right in the middle here. So we can measure, every measurement has uncertainty. That's a given because we don't have infinitely precise instruments. But what we do have, we need to work with, and we can make very accurate estimates, and we can calculate our uncertainty from them. So if I were to measure this, I would say it's 21, definitely 21, right? And then 21 point, or actually, sorry, not 20. Or yeah, it would be 20. Yeah, it would be 20. Since burettes are read opposite, so in terms of the volume left, it would be 20 something. If you're, or sorry, the volume removed from it, it would be 20. So let's say this goes up to 0, and you go down to 20. That means the volume removed from the top was 20, and you end up with 5 left. But let's just read this measurement right here. This is 21 down here. So it'd be 21.5. I would say it's 20.15, like that. Oh, sorry, I meant 20, 20.1, 20.15. So it's somewhere between 0.1 and 0.2, right there. But you don't know for sure. So I give this to each one of you, and one of you gets, oh, I get 20.15. One of you gets 0.14, 0.16, 0.17, whatever. The key thing here is that if everyone did it correctly, you're supposed to get 20.1. Those are the certain digits. Those digits you can determine from the tick marks alone. It is definitely at least 20, at least 21, or sorry, at least 20, at least 20.1. So it's 20.1 something. That uncertain digit, that one, that 20.15, that is called your estimated digit. So I'll write that. Estimated digit. So with each measurement, you have this degree, this 1 decimal place of uncertainty called your estimated digit. And it's totally okay for that to vary, and for you to get a different number than someone else, and for you to use that in an actual calculation. It's okay to have, it's accepted to have 1 estimated digit. Because overall, it does make that's like a scientific rule, I guess they just decided on. Oh yeah, we'll give them an estimated digit. It'll make the measurements be more accurate. And it would, because this definitely isn't 20.1. It's definitely more than that. 20.15 or 6 would be more accurate. So yeah, I hope that makes sense. So you have your measured number, your measured certain digits right here, and then you have followed by 1 estimated digit. So you can only have 1 estimated digit. So another way I like to describe it is use the tick mark, go 1 decimal place beyond the tick marks. So meaning 1 decimal, in between tick marks, you can guess 1 decimal place in between tick marks. Okay, so now that we know how to take measurements, sometimes these measurements might have a different number of digits, and you have to add them, subtract them, multiply them, and you don't know which amount of digits to keep. This is where significant figures comes into play, or sig figs. Now, there are rules when it comes to sig figs. In a measurement, all numbers that are not 0 are called significant figures. So 1.5, for example, has 2 significant figures, 2 sig figs, because those numbers are measured. They are measured by somebody and they have a purpose. They hold a place value that is not 0. Then there are zeros. Sometimes zeros are significant and sometimes they're not. When you have a 0 on the inside of a number, it's like what we call sandwiched zeros. These sandwiched zeros are considered significant. And the reason why is because they are in between two important measured significant digits. Therefore, they are important in the measurement as well. So there we go. That's interior 0. Sandwich zeros are significant. Now, leading zeros are not. Where's the lagging zeros? 1. All right, whatever. So leading, and I should put and lagging. Without decimal. I'll explain this. All right. So leading zeros, we'll start with that first. Leading zeros are not significant. Okay. So in this number, 0.001050 has 4 sig figs, right? Only here. Not this. These are not measured. They are just placeholders. Let's say you're, or I'm not going to go into that. I'm going to go on a long example. I hope that makes sense. But these are placeholders. If I put another 0 here, I can put as many zeros as I want. It doesn't change this measurement at all. It doesn't make it more precise, less precise, or do anything to it. It's the exact same measurement. Therefore, whatever digits that are zeros I put in front are not significant. So now let's look at lagging zeros. Let's say if we just had the number 5,000, just 5,000. How many sig figs do you think 5,000 would have? Somebody could write it in the, or a couple of you can write it in the response box, the chat. Okay, I see mostly 1, some 4, but the answer is 1. And the reason why is because just like these small decimals, really large numbers without a decimal point, these zeros are just placeholders too. Maybe I'm on a meter stick, or maybe on some kind of measuring stick that measures only in thousands. Maybe it's like that. And I can't get any of these digits. Let's just say that. So if that's the case, I can measure 4,000, 5,000, and there's only one significant figure. I can't measure other numbers. So that's an example of the lagging zeros. Now, if I simply just do this, add a decimal, that changes the game. Now, those of you who said 4 would be correct because I added a decimal point. The decimal point is significant. I'm not in terms of significant figures, but to our knowledge and our understanding, it should be significant because that tells the reader that whoever wrote down this number knew that it was 5,000 point something. They knew it was 5,000 point. They knew that it wasn't 5,500. They knew that it was 5,000 point. So therefore, all of these would be significant. If I added another 0 and another 1, those would also be significant. That means you measured so accurately that you can tell that, oh, the 10th place is definitely a 0. I measured it. The 100th place, same thing. It's a 0. I measured it. These would also be significant. So in this number, there would be 6 significant figures because of that decimal and because these are trailing zeros or lagging zeros. I'll put trailing, not lagging. Trailing. All right, so good. I hope that makes sense. Are there any questions on that? Because we're going to apply those rules right now.
I have a question.
Yeah.
So let's say that those 5,000 we wrote differently. Let's say 5 times 10 to the third.
Right.
Would the significant figures change?
No, it
would
would be exactly the same.
Okay. Even
Okay,
if
so
there was no decimal compared to a decimal?
So yes. And so in this case, good. Good question. So if you have, okay, so the bigger number, the bigger or smaller numbers, let's go back to here. So you can convert those to scientific notation very easily. So let's take this number that was in the original example. This would be, oh, they did it for you. This would be 1.050 times 10 to the negative third, 4 sig figs. 5,000 would be 5 times, or normal 5,000. So that's not the eraser. I got this. All right, so 5,000, normal 5,000. 5 times 10 to the third. 5 point times 10 to the third, which is what you're asking. The sig figs wouldn't change because whatever's in the 10th to the third wouldn't be, well, it's not good to do that. So, okay, so 5 point is not really common nomenclature. Whenever you see a decimal, there should, at least in science, there should always be a number after it. So you wouldn't really see 5 point, you would see 5.0. In that case, it does change. And Daniela, to answer your question, yes, you count the trailing zeros when there is a decimal. Correct. That's exactly, yeah, that's exactly the point. So good. So if this was 5.0, then you have 2 sig figs. But if it was just 5 point, it would stay the same technically, but you wouldn't write it like that. So yeah, so you normally write it like that. Okay, so I hope that answers your question. Yeah, good question. Yeah, okay. Yeah, in science, we always write the 0 after the decimal. Okay, so any other questions? Oh, here's trailing zeros. After a decimal are significant. Zeros at the end of a number written without a decimal point are ambiguous and should be avoided using scientific notation, just like we talked about. Okay. All right, so scientific notation and exact numbers. All right, so, or not notation, figures. Now, exact numbers are definitions and counting, basically. So if you had, and we don't consider, so there's measured numbers and exact numbers. Everything we just talked about with numbers of significant figures are called measured numbers. Exact numbers, I like they use a stupid definition of exact numbers have unlimited number of significant figures. No. I like to say none of their figures are significant because they're not measured. Measured numbers are the only things that have significant figures, because you need to use those significant figures to add and subtract and multiply. You need to use those rules. But for exact numbers, it's just whatever you round it to. So it's not really like anything is significant. They're just definitions. And those definitions, what I mean is either something that's counted, like people. If I can count, there is 29 people, including me, in this chat room thing, in this Zoom room. So we can't, it's not 29.000. It's just 29. We can't say, we're not measuring people to the tenths, we're just counting. And by definitions, I mean mostly conversion factors. So 2.54 centimeters equals 1 inch. Let's just say there is more numbers to this. Let's just say this was the actual definition. We can't say that 2.54 in centimeters equals 1.0 inches. No, it is an exact definition that this equals this, or 12 inches equals 1 foot. It's not 12.00 inches, it's just 12. 12 of them equals 1 of them. So it is a definition from the conversion. Equations are another one too, like radius of a circle. Yeah, so it's diameter divided by, I don't like that example, whatever, divided by 2, right? You're dividing it in half, not by 2.00, just by 2, because it's definition. Okay, now another thing about, now that we know sig figs, we have to know how to do operations with them. So here we go. We'll just jump right into it. For addition and subtraction, it is not about the number of significant figures. It is about the number of decimal places after, or the number of decimal places that are used in the number. For example, we'll use this as an example. We'll use a different color. Red. Cool. So let's just take this. You have a number with 2 decimal places, a number with 3 decimal places. If you took these measurements, let's just say out of the context of this problem, and they were actually measurements on a meter stick or a stick, you can't add this number, the 2 decimal place one, to the 3 decimal place one and have 3 decimal places in the answer. That's because this number does not have that degree of certainty, doesn't have the thousands place with a digit. That means this digit is a question mark. That could be anything, it could be 1, 2, 3, 4, 5, whatever. So it's not good to say to round to the more, we can't round to the more precise place. We can only round to the least precise place. So you're only a team is only as strong as its weakest link, thing like that. That's basically what we're doing with adding and subtracting these measurements, and also multiplying and dividing. They're only as strong and as precise as their weakest precision point. So keep that in mind. Now, if we had the entire problem, we have a 2 decimal place added to a 3, added to a 3. Our answer would have to be in 2. So we would round that answer, in this case, 0.214 would be rounded down to 0.21. So that's that. Here's another one where you have 1 decimal place and 3 decimal places. Our answer has to be in 1. Sometimes, and I think you'll see this in the homework, you'll have numbers like this. What does this equal? So anybody want to tell me, based on significant figures, what this equals? Either by saying it or in the chat. Not 520, believe it or not. Not 520.2. Anybody else? Any other guesses? 500. Ding, ding, ding. Sarah Guerrero. Extra credit. Not 702. Oh, sorry. This is a decimal point. I was like 702. No, yeah, it's a decimal point. Okay. But yeah, 500. The reason why is sig figs. The decimal place that this 500 go, there's no decimal place there. The most accurate place 500 is to the hundreds place. The most accurate 20.2 is to here. Add those numbers together. Yeah, in the calculator you get 520.2. But in sig figs, the actual most accurate measurement you can take by adding those numbers would be 500. It would round back down to 500. Because you can't say this digit and this digit is real, because they're not significant figures. If you did this, then of course you can go to 520. But we didn't do that. I'll just Control Z, Control Z, Control Z. Okay. All right, so does that make sense? That's probably the most difficult thing about adding and subtracting with sig figs. And that's how they try to trick you on the exam and on the homework. So definitely keep an eye out for that. Any questions? No? Okay. Cool, so there's more of that. Now for multiplication and division. It's a little bit easier. Basically what you do is you take the least number of sig figs in every number that you're multiplying or dividing, and you use that number of sig figs as your answer number of sig figs. For example, 5.02 sig fig, or no, 5.02, 3 sig figs, 5 and 2. Our answer will be in 2, the least amount. 4 and 3 sig figs, our answer would be in 3. That's it. So that's it for that, for multiplication, division, and addition, subtraction. Sorry, I'm blanking. Okay, another question you might have. What happens when you have a lot of operations, more than one? So what you would do is you would use PEMDAS. So remember your order of operations, because the homework, the regular homeworks, I'll give you a hint now. is it will have one that's pretty difficult. And also in general, the regular homeworks are pretty intense. So do as best you can. That's why me and the TA are here to help you. So, and also another thing I suggest, make a group chat, maybe with the other members of the class, or when you go into your breakout rooms or something, when you're working on the worksheet, make some kind of group chat. You could talk shit about me if you want, I don't care. But the idea is you want to help each other with this stuff when it gets difficult. This might not be difficult, but it gets harder. So definitely be, do it as a team. Like, yeah, you know what I mean. All right, so complex operations, you're doing it the same exact way as the individual operations, but using PEMDAS. So the order of operations. In this case, we have a parentheses right here, and in subtraction with 2 decimal places, 1 decimal place. That means our answer would be, wait, this might be wrong. Oh, no, it's not. Okay, so you do, yeah, I was looking at it. I'm like, that's not the way I would write it. So what you would do, I'm going to rewrite this. Okay, so you have 2 decimal places, 1 decimal place. That means our answer, 1 decimal place. I'm going to take this out. So our answer would be in 1 decimal place, 3.4. So we are multiplying a number with 4 sig figs to a number with 2 sig figs. Therefore, our answer of those multiplying together will be 2 sig figs. Or, sorry, yeah, 2 sig figs. The answer would be 12, and it would be 2 sig figs. So that's how it works. You're just doing the rules for each operation in the correct order, and until you get to the end. So, yeah. And you're rounding on each step. Some people say, oh, it's better, you get a better answer if you don't round until the end. For sig figs, we need to round at each step because that is the correct way to do it. But for a lot of physics problems, I'd say only round at the end. And I think for a lot of things in this class, I say round at the end. But for sig figs, we can't. Okay, any questions? No? All right, then we talked about this already. All right. The last part and probably the toughest part of the chapter is going to be unit conversion. So unit conversion, we are using conversion factors to convert from one unit to another, or using multiple conversion factors to do that. So let's just cut to the chase with an example. So we're converting 4.2 inches to centimeters. So let's just write this out. So 4.2 inches to centimeters. Click, there we go, centimeters. All right, so what do we do first? Step 1 is write measured number. Our measured number that we're trying to convert is always the thing we're trying to convert. 4.2 inches, all right? 4.2 inches. What do I do next, Professor? Step 2, identify conversion factors. All right, let's say this problem gives you 1 inch equals 2.54 centimeters. I identified the conversion factor. Step 3, or this might be factors. Yeah, factors. In this case, it's only 1. There might be, and I'll put slash, write a plan. So in this case, all right, I'm taking the inches, I'm directly converting them using this conversion factor to centimeters, and then I get my answer, centimeters. Sometimes you need to convert in 2 steps or more, which we'll do in the next example, but let's just do one at a time. So 1 inch to that, and then you do set, then you set them up to I'll put set up to cancel units and solve. All right, so what I mean by that, our units that we don't want in our final answer need to cancel out. And the way they cancel out, one of them is in the numerator, the same unit is in the denominator. So I know I need to use this conversion factor to convert 4.2 inches to centimeters. So I know that inches, 1 inch, has to be in the denominator in order for inches to cancel out. Then I put in 2.54 centimeters, and then you solve. You see how inches cancels with inches? And then our only remaining unit is centimeters, and you get, what is it, like 7, 8? No, not 7, it's probably like 9 something. Oh, 10, all right. So you do that, just like how they did it, and you get 10.668, but our measured number, 4.2, if you remember, is in 2 sig figs. So our answer is also in 2 sig figs. Yes, Brandon, 11. Good. Good. All right, so does that make sense? Is there any questions on how I set that up? That was a pretty easy one, but if there's questions, no problem. Don't ever think your question's stupid, because I'm sure if you have the question, somebody else does as well. No? All right, then we'll do a 2-step one, and then we're almost done. Is there a tougher one? We'll do a tougher one. Yeah. That's not too bad. And we'll do this one. Okay. Oh, I give you the answer. Damn it. Hold on. All right, now you can't see the answer. So what is the mass of, okay, I guess we'll see the answer. Oh, Danielle, that's a really good question. So do we need to use sig figs if we are not asked to? On the homework, okay, here's the deal with the homeworks. The homeworks, they specify when to use the correct, and I suggest like write this down and remember it. If there's a number of sig figs they want, they tell you. If they don't tell you, assume 3. Sometimes they don't tell you, but they want their answer in 3, or else sometimes they might mark it wrong. So to answer your question for the homeworks, just pay attention to each question. If it doesn't specify, use 3. Me personally, I don't care if you're asked to or not. On the exam, the correct answer, oh good, Gustavo, good. Yeah, we're on the same wavelength. On the exam, the multiple choice questions will have the answer in the correct number of sig figs, because that is more accurate. And that's the correct way to do it standard wise. In a open-ended question, if you write the wrong answer in sig figs, I will not take credit off, because I understand how difficult, and you're trying to figure out a more difficult problem, and you have to worry about sig figs, which aren't really that important. I understand that. I won't take off any points, but you should still know how to do it for the multiple choice questions. For example, if the answer is 5, if you get 520 and you see an answer choice is 500, like we saw before, you might want to think, wait, is it because of sig figs it's 500? If so, that's the right answer. So you want to at least know how to do it so you can select the right answer. Okay, so let's look at this one. What is the mass in kilograms of 173 blah, 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 liters of jet fuel whose density is that? So we have the liters. We write this down. So I'm going to do it side by side with them. So we have the liters. We're going to write it down. 173,231 liters. We want to convert it into mass or grams. We have the density of it. So we have density is also a conversion factor. We have 0.738 grams is in every single milliliter of this. We have this many liters. All right, we can do it multiple ways. Let's do, since we have the grams in 1 milliliter, let's just convert this to milliliters first. That might be a big number, but we can do it. That's kind of a different way that they're doing the same thing. Okay, they're doing the same thing, fine. But there's different ways to do it. You could do this step first. If you did, yeah, either way you set this up, it can work. It depends on how you think. So I see, liters, I can easily convert that to milliliters. I know from my prefixes that 1,000 milliliters equals 1 liter. So I would write down 1,000 milliliters here is 1 liter, and then the liters will cancel. Then I will take the milliliters And I know, what do I know? I know 1 gram, I know this many grams is 1 milliliter. So I want to cancel out milliliters. So I'll write that second step down here. Well, this multiplied, I'll write it out over here. 2, 1 times that over 1 liter times, we want milliliters to cancel out, so we're putting 1 milliliter in the bottom, and we know that 0.739 grams is the mass in 1 milliliter, and then what is the mass in kilograms it's asking for? Oh, so we don't even know. So that would give us the mass in grams. This would cancel, oh, no. So the liters would cancel with liters. Milliliters would cancel. Now the grams, we know that 1,000 grams is 1 kilogram. So you write kilogram on the top, 1,000 grams on the bottom. Grams will cancel, and you get your answer. So the idea here is to make sure you're doing it right, you want the final unit that you want your answer to be in to be the only unit that's not canceled out. Everything else needs to be canceled out if you did it right. So if you do that, your answer is whatever is underneath that. 1.33 times 10 to the 5th kilograms. And you see how we use sig figs because, wait, did we use sig figs? Actually, no. Oh yeah, we do. Yeah. So, well, it's arguable because technically the only measured number that's in here is this one, the big one. This density is an exact number. It's a conversion factor. So technically you could use, well, I think the answer would be right if you use 6 sig figs. So maybe they used the wrong sig figs here. So either way, I wouldn't mark it wrong, and both answers would be very close to each other. It would be 1.33, etc. More stuff. And I would never put on an exam 2 answers that are close together to trick you about sig figs. I'm not that mean. So I'm not mean at all, I don't think. But unless I make a bad joke, that may seem mean. Anyway, any questions on the longer ones? I don't know why I just saved it. I don't know why I did that. That's all. Oh no. Okay. What's going on? That's just my natural instinct to save everything. So anyway, any questions? All right, we'll do one more example and then we're done almost. Yeah, so we're gonna do a problem which may appear on the homework, I think, on either regular or basic, where you have a unit raised to a cubic or even a squared. In this case, it's different than we normally did. So if you want to go from cubic inches to cubic centimeters, or cubic centimeters to cubic inches, here's what you know. So you know that 2.54 centimeters is equal to 1 inch. You cannot say that 2.45 cubic centimeters is equal to 1 cubic inch. That's not true. What you do is you cube the whole thing, and then you make that true. So if you cube it, you get 16.4 centimeters cubed equals 1 cubic inch. That's how that works. And then you can use and you use that conversion factor to cancel out with other things. So just know that for cubics and for squareds, you'll just square the entire equality for it to work. So like that. Okay, any questions on that? We'll do one more. Oh no, here it is. They put the answer. Oh, I know why. I'm not in presentation mode. Yep. Okay, cool. Hopefully you didn't see that. But so suppose you count 1.2 times 10 to the 5th atoms per second. How many atoms would you count in 1 year? All right. So that's a big question. Oh no. Okay. So what we know is a lot of conversion factors. We have the 1.2 times 10 to the 5th atoms. So ignore this first part. So we write that down per second. So then you can do my mind, everyone could do this differently. But what I would think is, all right, if I figure out how many seconds are in 1 year, then I could just multiply it by the number of atoms and get my answer. That's exactly right. So you do that. So 1 year is, they use, okay, don't do this. I don't like this. Don't do this. All right, we're gonna change this. Because they're rounding everything with sig figs. I don't like that. Because in this case, that's just, you're rounding in every step and you're just getting the wrong answer. All right, so here's how we'll do it. Or I'm just gonna write it because I have my pen. All right, so you have how many seconds are in 1 year? 1 year. And we're going to multiply that number by the atoms per second to see how many atoms you count in a second. 365 days, 1 year. That cancels. 24 hours in 1 day. Days cancel with days. 60 minutes in each hour. Hours cancel. 60 seconds in each minute. Minutes cancel. So now we have our years converted to seconds. Times 1.2 times 10 to the 5th atoms per 1 second. Multiply all that together and you get a number. Let's see, I'm going to do it on my phone. 365 times 24 times 60 times 60 times 1.2 or 12000. I got 3.78 times 10 to the 12. Okay, cool. That's right? Yeah, okay, cool. So I got 3.78 times 10 to the 12. What did they get? They got something different, I think. Maybe they rounded and it just worked out well, but anyway, that's what you get. That's the best way to do it. So any questions on that? Between that and the cubics, that's probably the most complicated it'll get for now, for sig figs and for conversions. Okay, if not, then here's one. So find the density of a metal cylinder with the mass of that, length, and radius of that. Okay, so sometimes you might need to use formulas to figure this out. So volume, and this is of a cylinder, and also these weird equations, you can look them up and give them to you. Like volume of a cylinder, who really remembers that? So volume of a cylinder, pi r squared L, right? You have the length of the cylinder, you have the radius. Automatically you could find the volume. So you do that first, and that's exactly what they did. So you find the volume. Then you're looking for the density. The cylinder weighs 8.3 grams. Its volume is that. So you just divide the two, and you get the grams per centimeter cubed. Since the mass, all these are all measured numbers. Since the measured numbers have 2 sig figs, 3 sig figs, and 2 sig figs, and all we're doing is multiplying and dividing, our answer has to be in 2 sig figs, like that. Okay, so that's it. That's it. So is there any questions? Any questions now? I'll field all questions. Nope. Okay, no from Gustavo. All right. So if there's no questions, I hope that went well. I hope it wasn't too slow. It probably was for some of you, especially those of you who said you're in your last year. Like, I'm sure this is really basic, but now what we're gonna do is we're going to our breakout rooms. I'm gonna make them. I'm gonna do, let's see, there's 28 of us, so I'll do 7 breakout rooms, so 4 people per breakout room. And it'll be random breakout rooms. So what that means, and what you can do in your breakout rooms is you can go to Moodle. So hold on, I'm gonna show you Moodle. I'll show you where to go. So new share. Where's my internet? Here we go. So can everybody see my Moodle now? You should be able to. So in Moodle, you should see this, and you see here we go, warm up basic homework. Click on it and you do it. And it's very,
I have a question about the homework.
yeah, what's up?
So I'm trying to click on the red boxes for extra help on the bottom parts, and it's not opening the window correctly.
For the for which assignment?
For the first assignment.
The warm up
Just the-
basic?
Yeah.
Okay. Let's see. Wait, where at the bottom? Oh, this thing?
Yeah, any of the help boxes are just
Not fine.
broken.
Like does it say this?
Yeah.
Oh, that's probably because there is none. Because it's a warm up homework. Maybe,
Okay.
but let's double check that right now. So I'm gonna go into the next homework. Let's do. There should be help in here. Oh, some of you already started it already. Wow. There we go. See, for the other ones it works. I guess for the warm up basic, there isn't any because it's very simple. But for
Okay.
the other ones there are. So good point. Okay, cool. Any other questions? So right now you're gonna work on the warm up basic homework. It's due tonight. I'm just gonna count it for 1 participation point. So yeah, any other questions? You make your own exams or NJT standards. So I make my own, but a lot of them are from NJIT questions. And if you're asking that to see, oh, does he use old exams that are similar? No. So I'm sneaky with that. I make sure they're not. But some of them I do get from my colleagues at NJIT. So, okay. Now I'm going to do the breakout rooms. I'll make 7 of them and just mingle with your group. And maybe one of you guys could share the screen and just go through it together. And then everybody else could do it on their own screen or that's it. And I'll close them at 12 and then you can leave after. You can leave when you're done. This is a really basic homework. It might take you 10 minutes, but you can leave when you're done. Marilyn, before the exam, do you have the review class? Of course, yeah. So before the exam, I have study guides for each exam. We're gonna go over in depth and you can ask questions on that. So I try to give you guys a lot of resources. Something else that I do, I'll tell you guys right now, is I have this thing on Instagram called Crash Chem that I made a couple years back. I'll put the handle somewhere here. Now you can see my PowerPoint. You should be able to, or my screen. Yeah. So move that over there. So I made a thing. It's called @CrashChem. And why is it being difficult? So what I have on there is like 30 to 45-second videos of me explaining really important concepts such as mass and matter, whatever. There's a bunch of stuff on it. I think it's like 30 videos so far. I keep making more. And they basically very quick, to the point explanations of how things work. Because what I found is a problem throughout the years is I give YouTube video links to my students, and you go on Khan Academy or something, and it's like, hey guys, my name's Ron, and like this is my first video, and like today we're gonna learn about. But the idea is it takes like 3 minutes for them to actually start explaining stuff, and that's a pain in the ass. So what I did was I just cut right to the point, explained everything that's important, and then that's it. So I put that on Instagram. It's easy for everyone to access. And that's a resource I have that I made. And then I do review classes before the exam. That'll be at the end of a chapter. And it will only be like a 15 to 20 minute review, not too long. And yeah, so that's it. Also, I give YouTube video links at the end of my slides. I don't think I have that for chapter 1, but for the other chapters I do. Okay, any other questions before we break out into the breakout rooms? What's the @? Oh, it's like for Instagram, like the Instagram handle. Like, yeah. So any other questions? Or you can just go on Instagram and search Crash Chem. You'll still get to the same place. Or go on Google and search it. All right, cool. So one more question from one of you guys. Do you provide extra credit throughout this? Of course. So let's go to the Moodle again. And, oh, I offer a lot of extra credit. if you read my Rate My Professor, that's what they say. They say, oh, he gives a lot of extra credit. So here's chapter 5. We have an extra credit assignment. And then towards the end, we're going to have a lot of Moodle homework assignments. And I made 2 of them extra credit. And then all of these are going to be extra credit. The chapter 12, 13, and 14 homeworks are going to be extra credit because those are not on the final exam. So I'm going to make them extra credit. And we're going to be cramming them in because we just don't have enough time to learn all this stuff, all these different chapters. But it's going to be unfair to you to make them do. So I'm just going to make them extra credit. And it'll definitely help you towards the homework part of the grade. So, okay, cool. So I'm going to break out into the breakout rooms, and me and the TA will go to each room and see how you guys are doing. And then once you're done, you can leave and whatever. So it was a fun first class, and I look forward to Wednesday. So I'm going to open all rooms. All right. Now you can join the rooms. I'm going to turn off my video. I'm hungry. So definitely go to your breakout rooms if you haven't already. You should have a thing that says to go to them. Oh, one unassigned. Who's unassigned? Oh, Armin is unassigned. Assigned 2, put you in breakout room 5.
Hello? Yeah. Mute and unmute yourself. Can you hear me on the thing? All right. Can you also try unmuting yourself? Unmuting yourself. So on the bottom left, unmute yourself. Or bottom left, there should be a join audio. Wait, there's not an audio? Okay. Do you? It's probably because you don't have a mic. You don't have a mic, like a microphone, built-in microphone. Oh, I don't know how, but I joined a different breakout room. All right. Good luck, guys. Bye.